We've mentioned in a couple of different videos that when you are dealing with exponent power rules that you have to be careful when you are applying the power to make sure that you do not have positive and plus and minus operations or addition and subtraction operations in the base, as we see right here. And so the question that we want to establish is what constitutes the problem here. When we look at this, we readily recognize that when we have multiplication or division operations in the base, as we see right here, x times y, we can split this up into x squared times y squared appropriately. However, what we will come to find out by the end of this video is that we cannot do this. X plus y, the quantity squared, does not equal x squared plus y squared. And we want to establish that this is mathematically correct. So as we look at this, let's start off with the one that we know is correct. And we see here x times y, the quantity squared. And let's establish what's going on here mathematically. The square indicates that the base is multiplied together 2 times. And by doing so, we can use the commutative property of multiplication to rearrange the factors, and this gives us an equivalent expression, and we end up with sets of factors giving us x squared times y squared when we recombine the like bases. However, when we're dealing with a situation where the base has an addition or subtraction operation, as in the case here, x plus y, the quantity squared, what we're going to find out is that when we expand this out appropriately according to the rules of the exponents, that we encounter the distributive property from algebra. So we have to apply the distributive property here to get the correct terms. This one here is applicable to the FOIL method, as you remember from algebra. The first terms are multiplied together, giving us an x squared term, followed by the outer terms being multiplied together, giving us an xy term. Then the inner terms are multiplied together, giving us a yx term, but they are interchangeable, or they will commute with each other, so we have a second xy term there. And then finally, the last terms are multiplied together, giving us a y squared term. As a result, we see that when we have x plus y, the quantity squared, we are equal to x squared plus 2xy plus y squared, and that is the correct expansion. In comparison here, what we see is that whereas when we have multiplication operations or division operations within the base, and you can essentially assign the power to each individual term, when you have addition and subtraction operations, you cannot do this. We have established that x plus y, the quantity squared, gives us x squared plus 2xy plus y squared, and we can see that this is definitely not equal to x squared plus y squared. So we should have established by now that when you have addition and subtraction operations inside the base, you have to execute your expansion of the exponent and apply the appropriate distributive rules to the structure.